My name is Yangjun Wu, and I will present our paper, Keypoint Cascade Voting for Point Cloud-based 6-stop pose estimation. Most existing machine learning-based 6-stop pose solutions focuses on RGB or RGBD input data, possibly since CN was originally designed for images, and depth sensors were relatively expensive compared to single RGB sensor. With the advantages of techniques, CN focused more on data such as point cloud rather than images, and the depth sensor became more affordable. This motivated us to develop a pure surface geometry-based 6-stop pose method, which is called RCVPose3D. RCVPose3D was developed based on our previous work, RCVPose. RCVPose was a keypoint radio voting-based method. During training, an RGB image is forwarded into a fully convolution ResNet. The network estimates a symmetric mask and a radial map. The radial map saves the Euclidean distance from each of the key points to each of the object points. A straightforward L1 loss supervises the learning. At inference, the pre-trained network estimates both elements simultaneously. Then the symmetric mask is used to filter out the background pixels in the radial map. Afterwards, the estimated radial map was forwarded to a 3D voxel voting module where votes were accumulated by rendering spheres. The estimated key points was located at the peak of the accumulated space. At last, Horn's method estimated the 6-stop pose based on the estimated key points with an optional ICP at the end. Similarly, RCVPose3D used radial voting to estimate key points as well. However, it focuses on pure geometry information from point cloud. A novel cascaded architecture is proposed in order to optimize the current problem parallel structures. Further, a novel loss function based on the geometry constraint of key points is added as well to enhance the learning of the network. Finally, a novel score for the machine learning voting method is introduced to fasten the fine-tuning cycle of the training stages. The most common existing architecture of 6-stop pose methods are all parallel, meaning that multiple tasks are learned simultaneously, just like the EDSM in the diagram. However, in 6-stop pose, majority of the points are background points. Foreground points only takes a portion of 10 to 30% of the entire point cloud. This motivated us to develop a cascade structure. The network segments the object out from the scene, denoted as EDS initially, and then the regression portion estimates the voting quantity, in our case radii, only on the region of interest estimated. This allows the network to focus on these points only within the ROI for the regression part. Our experiments showed that it is more accurate compared to the parallel structure with a similar capacity, at least similar number of trainable weights. Despite the architecture, we look into the geometry constraint of key points as well and propose a loss function named radial pair loss. Most previous keypoint voting methods only designed lossing between ground truth and estimation. However, the key points are not independent. They are linked with each other with certain geometry constraints. The radial pair loss considers the offset of distances in between estimated and ground truth key points locations. This loss function helps the network to converge further when it is close to saturation. Border confidence score (VCS) is a novel score we introduced in order to fasten the cycle of training, especially for hybrid methods, when the classical algorithm is not as parallel as the ML part. Therefore, an intermediate matrix estimating the performance is significantly important for fine-tuning of hyperparameters. In order to evaluate the estimated radii, we calculate the portion of voting quantities within the threshold epsilon compared to the total number of votes. Epsilon here depends on the ultimate evaluation matrix. The key point location will be more accurate when the voting space is more confident. We evaluated RCVPose3D on two core datasets, YCV video and occlusion line mode. Firstly, we tested various existing feature encoders for point clouds. Then we evaluated fully with ADDS matrix for occlusion line mode and ADDS AUC matrix for YCV video. Our method achieved sort-of performance on both datasets when using pure geometry information only. We ranked the first on the slightly strict ADDS AUC matrix of YCV video based on our literature studies. Here are some results of the method. Note that all RGB information here is for demo purpose only, and again, we focus on pure point cloud geometry. Our paper included more details of our experiments supporting our theorem. For example, we compared the performance of parallel versus cascade architecture with similar capacity. We measured the consistency of VCS and ADDS matrix. Further, we investigated the impact of the number of points, indeed, both of the regression part of the network. Finally, we also explored various ML descriptors, including two hybrid encoders embedding classic feature descriptors PPF and FPFH. In conclusion, we are one of the early birds taking a point cloud with pure geometry info to estimate 6-stop pose using CNN. We propose a cascade architecture which improved the accuracy with slight speed trade-off. We propose a geometry constraint radial pair loss to further improve the performance, and VCS, a confidence score, to improve training for hybrid methods. Lastly, we achieve sort of performance with notable improvements compared to existing methods. Thanks for listening. Please refer to the paper for further details.